Hi, passing scientist. I am Jorge, and I am back to do a physics problem from Wisconsin's University. It says the following: an orbiting space station is observed to remain always vertically above the same point on the Earth. Where on Earth is the observer? Describe the orbit of the space station as completely as possible. First of all, we have to be familiar with the concept of geostationary orbit. What does that mean? A geostationary orbit is the one that describes an object with an orbital velocity around, in this case, around the Earth. Okay? Sorry for the bad circle. Okay? So now, once we know that, imagine the situation. Okay? So we have the Earth. We have the Earth that turns around an imaginary vertical axis. So if we want to observe above the same point of the Earth, always the object, it has to happen the following. It has to happen that at the same time that the Earth rotates around the axis, okay, the object has to orbit around so as to observe the object always staying at that point, okay? So that just can't happen if we are on the equator, because think about it. I think you got it. We have here we are here. We have here the object. So we just are rotating at the same pace that the object does. What would happen if we wanted to have that situation in one of the poles, for example, in the North Pole? That's not possible, because in order to have that situation, the object should be at rest above the pole. So that would mean that the object will end crashing into the Earth, no? So once we are clear about this answer, where on Earth is the observer has to be on the equator. Now we have to describe the radius of this orbiting space station. How could we describe that? Let's draw forces here. We have the centripetal force, as well as the gravitational force, okay, a central force that attracts the object rotating or orbiting around the Earth directly to the Earth, to the center, okay, because obviously the Earth here is on the center of the circle, okay, fine. And obviously we have two acceleration here, the tangential acceleration and the centripetal acceleration, yeah? But let's focus on forces. So therefore we can say that the centripetal force in a circular orbit has to be equal to the gravitational force. So now we have that the mass of the orbiting space station multiplied by the velocity, that orbiting velocity, circular velocity, divided by the radius of the orbit, equal to the constant. Obviously the capital M is the mass of the Earth. And here I'm gonna neglected the radius of the Earth so as to simplify the problem, okay? Because if I didn't simplify it, we would obtain a binomial. So let's simplify it just to, but take that into consideration. Okay, so now, yeah, sorry, I screw it up. I almost just got screwed here. So now it's a squared and here now. So obviously, now what happens? That we just have to simplify right here, and we obtain that we are. You agree with me in this, okay? Let's do it in pen because I'm saying that it's better seen like that. So now we obtain this, but we want to go further in our description because it's saying to us that we have to describe it as much as we can, as completely as possible. Okay, so let's go further, and okay. So now we have the velocity. I mean, we have the velocity in function of the radius of the orbit, but let's do it in function of the Earth. So now let's imagine we take that mass on the Earth surface, okay? So obviously here the weight of the mass equals to the gravitational force, okay? That's completely the same. So now the mass of that orbiting space station per the constant equals to the gravitational force, the radius of the Earth in this case. Fine. Just have to do this, and let's just, okay, so we have this equation that we can plug into here, and we would have the velocity squared equals to gm. Sorry, gm is the thing that we want to, yeah, so we have this, and yes, we got this. Okay, we already have the velocity of the orbit, the velocity of the object orbiting around the circular orbit in function of the Earth's radius and orbit's radius. Well, we want to go even further. What could we do more? Let's think about the period, the orbital period. But for that, let's think about the angular velocity. The angular velocity is defined as a complete turn per the time spent doing it. So as we know that the 2 pi, and we know that that equals to the velocity and the radius of the orbit. So now 2 pi radius of the orbit, velocity. Once we know that, just we can okay, so we just have to go here and again plug in. Okay, equal to G. And fine, and we just have to describe the radius of the orbit as follows. Okay, so we are done. As you could see, it was a simple exercise, but quite important. So take that and try it and think about it. So as always, it's a pleasure. See you in the next one. We keep working. Bye.